Very good morning, students. Today I will introduce the another important lecture on the short channel effect, and that is related to your CMOS scaling that has been already discussed in the previous 3 or 4 lectures. And what we have done previously or done till now. In the module 1, we have done all the semiconductor details along with your Schrodinger wave equations, Bloch theorem, chronic-Prenny model, Birwin zone, everything, every new parameters what have been incorporated in your syllabus, all have been discussed very clearly and very thoroughly, right, in the module 1. And in the module 2, we have started our lecture with scaling. And based on scaling, why scaling is needed, how scaling is done, and based on that I have already discussed the constant electric field scaling, and in a previous lecture I have discussed that constant voltage scaling, right? And what are the primary scaling factors of these constant electric field scaling as well as in constant voltage scaling, all have been discussed very clearly. Okay, and what are the primary scaling factors? That is oxide thickness, that is width, length, acceptor concentration, donor concentrations, that is nothing but the doping concentration, and your supply voltage. So how it is scaled, and related to that, how delay can be calculated, how power can be calculated, everything, every basics that are needed for getting understand the basics of scaling, that all have been done already, right? And I had also discussed the another important factor, that is the non-scaling factors, and that was the band gap of the silicon, that is the thermal voltage, that is the velocity saturations, that is the parasitic resistance, everything I had discussed about the non-scaling factors. And one important thing I also told, that whenever I talked about this thermal voltage, and it is a relation, the thermal voltage is a relation is kT by Q, right? And where K is the Boltzmann constant, and it is a very important metric of the device because it defines the sub-threshold slope, right? And from which we define the leakage current of the device. So it is a very important factor and which cannot be scaled. So among the non-scaling factors, so this is a very important metric, that is the thermal voltage. Because of that, why is the reason? Because from this thermal voltage, from this expression and the subthreshold slope, we can define the leakage current of the device. So all have been discussed in a deep level in my previous lectures, right? So there is a little bit of recapitulations that what we had done and what we will do today. Today I will discuss all about on the short channel effect. I think that you all have heard this term whenever you were taught the analog electronics device, solid state device, because nano electronics is basically all about the device. Because if you don't have the very basic knowledge of the device, so it will be little bit harder for understanding the concept of scaling, the beauty of the nanoscaling, right? So we have to know very detail of the device along with these important metrics, important parameters that has been done, that is scaling, that is short channel effect, that is velocity modulation, channel length modulation, everything. And these are the extra. This is not in your syllabus, but for cracking the GATE examination or any other higher standard examination, you should have the knowledge of that, right? Because most of the important questions are coming out from that field, and that is a very core field of electronics and communication engineering. So you should have the knowledge. Should have the knowledge of that, what I will discuss today, and one of the important topic, that is the short channel effect, right? Because this is an important topic of scaling, that is related to scaling. So that's why I am discussing it. And also I have already shared one PDF that is the nanoscale MOSFET. And in order to understand the nanoscale MOSFET, you should have the idea of short channel effect, right? So that's why by assuming all aspects of your standard, I will discuss the short channel effect once again, and it's also very much helpful for your gate, and there are so many important formulas are there. By using that, you can easily calculate the problem and find out the answer that frequently come in the gate exam, right? So so let's start our lecture on this short channel effect. In the last lecture, we have seen the different scenario of scaling, right? And we had also discussed about the new non-scaling factor that I have told a little bit ago. And now we will discuss that what are the challenges in scaling, right? I have written over here, that is, what are the challenges in scaling? Because whenever we go for something new, many challenges we are facing, and we have to handle these challenges, and we have to overcome these challenges in a positive way. So here also the challenges are there whenever we will do the nanoscaling, whenever we will do the miniaturization of the circuit, miniaturization of the devices. So this is a great challenge. This is a new challenge in this today's era, and we have to take this challenge. And one of the important challenge of that is your short channel effect. So what are the new effects that come to the picture, right? So first effect that I am going to talk about, this is a short channel effect. Okay, the first effect I am going to talk about is a short channel effect, and this is a very classic problem. Very classic problem. Why it is called a very classic problem? Because the threshold voltage, we all have the knowledge of threshold voltage, that is denoted by VTH, right? So this threshold voltage starts decreasing as the transistor miniaturization starts in the micron range. Got my point? So again I am saying that I am writing this point because this is a very important point. That is, so this is a weight pen. Okay, sorry for that. The threshold voltage, I think it's visible. The threshold voltage starts decreasing as transistor miniaturization starts in the micron range, right? Starts in the micron range. Okay, got my point. So what is threshold voltage in classical transistor? So this is my question. So what is the threshold voltage in a classical transistor? Because I am highlighting this point, that is the classical transistor threshold voltage. So what is that? What is the threshold voltage in classical transistor? And classical transistor means, I must say, this is a long channel transistor, because it is before the miniaturization starts. So it's a long channel transistor, right? So this is nothing but the classical transistor. Okay, so we will not properly derive, but we should have the knowledge of the threshold voltage in the long channel transistor, and from there we will discuss about the short channel effect. Okay, so without getting the knowledge of the threshold voltage, it is impossible to discuss the short channel effect. And in order to define the short channel effect, I will discuss many things in terms of energy band diagram, and very important parameter, that is electron affinity and your work function. Many new parameters should be incorporated in my lecture, and it's very important for your competitive exam, not in the semester, but you should have the deeper knowledge of that. So that's why I am teaching in a very detail. Otherwise I can skip everything. I can skip the important thing, but I think that from my end as a teacher, it's a very important to discuss all very basic in a deep knowledge. Okay, in a deeper level, right? Okay, so from the concept of threshold voltage, we will discuss the short channel effect. And short channel effect, which is also known as short channel effect, which we can also express, that is VTH roll off. you all know the meaning of roll-up. So there it is, VTH roll-up. So we can say it, we can rename it in this way. What is that? This is the short channel effect, right? Okay, so we must come to that point that what is the basic aspects of threshold voltage, right? Just I am giving the headline, that is the basic aspects of threshold voltage. Okay, so for everything, whenever we will I will deliver my lecture, I will use one picture very common, very frequently, and that is the device structure, that is a MOSFET structure, right? CMOS structure or MOSFET structure. And what is that? If we take the p-type substrate, so how you can define the p-type substrate? This way. This is a p-type substrate, and this is your N plus, this is your N plus, and this is your oxide layer, means SiO2, and this is your gate, and from which the terminal is the applied gate voltage is denoted by Vg, right? And this is the p-type silicon substrate, because the base is silicon. This is a semiconductor material, and where the acceptor concentration nearly equal to 10 to the power 15 per centimeter cube, right? Got my point? So before discussing anything, I will take help of this picture, otherwise we can't go, right? We can't further proceed to the another level. Okay, so what is this? So there is a distance between the source and drain are far apart. This is your source terminal, this is your drain terminal, and this is your gate terminal. So the distance between source and drain are far apart. This is nothing but the channel. Okay, so when we look at this long channel transistor, why we are saying this long channel transistor? Because the distance between source and drain are very high. Okay, so what will be the one-dimensional view? One-dimensional view means this one. This is your one-dimensional view. Because if we look at the Mos capacitor, right? You have heard this term before also. What is Mos capacitor? Mos capacitor means this is your metal, right? This is your metal, this is your gate terminal, this is your metal, this is your oxide. I am just writing over this term. This is your metal and this is your oxide, and obviously this is the semiconductor. So that's why it is called MOS. Why the significance of this term MOS? This is metal oxide semiconductor. So that's why this is the metal, this is the oxide layer, because we all know that the gate terminal is not directly connected to the substrate. There is an insulating layer in between, and this insulating layer is made of the oxide material, and that's why I am written this SiO2, because this is made of the material of SiO2. But materials are changing, device structures are changing, as well as we are going down to the nanoscale, right? That has been already discussed in our scaling part. Okay, so why it is called Mos capacitor? Because this is metal, oxide and semiconductor, and it's a capacitor because this is a charge induced. If we apply this negative voltage, it will apply positive, again negative, again here is positive. So charge induced effects are there, and that's why it is called the Mos capacitor. So why we said that this p-type substrate means this is an n-channel transistor, right? N-channel transistor, and if it is n-type substrate, this will be a p-channel transistor. So here it is showing that this is an n-channel transistor, and what gate voltage, what is the amount of gate voltage is required to turn on this n-channel transistor? The answer will be positive or negative. Yes, the answer is what will be the answer? You all know that it is an n-channel transistor, so we have to create a channel of electrons in between source and drain. So that's why we will apply positive gate voltage, positive threshold voltage, right? If we apply this positive voltage, I can say that if we apply this positive voltage due to this capacitive effect, here it is negative, here it is also positive, and here it is negative. So that's why it is called the Mos capacitor. Okay, so threshold voltage is nothing but to alter the doping concentration. It's a very important point. So why threshold voltage needed? Because threshold voltage, I think is visible. Threshold voltage is nothing but to alter. I will share the PDF of this. I am total lecture, so don't worry about that. To alter the doping concentration. To alter the doping concentration. Now, listen carefully. Listen very carefully. I will discuss some points, some important points in the higher level also, but this should be kept in your mind to because it will help you later. It will help you later whenever you will do the research. Okay. So basically, I think that you should have the idea because you have already studied the device, semiconductor device, solid state device. So that's why with general rule is that because we are concentrating is this doping concentration means this P is equal to, in general, it is 10 to the power 15 per centimeter cube. And what is this P? This P is nothing but whole concentration. Right, this P is nothing but a whole concentration. So how can I calculate what is the amount of electron concentration needed? Right, so we will use the very basic formula, very old formula that you all know, that is NP equal to Ni square. Is very known to you. NP equal to Ni square. And what is Ni? Ni is nothing but the intrinsic carrier concentration. And what is the value at room temperature? The value of room temperature of Ni is 10 to the power 10 per centimeter cube. Okay, so we know the value of whole concentration. We know the value of intrinsic carrier concentration. So in this way, we can also calculate the electron concentration, that is N. So what is N? N equal to Ni square divided by P. And what is your Ni square? Because Ni at room temperature is 10 to the power 10. So it will become 10 to the power 20. And this is your 10 to the power 15. So it's nothing but 10 to the power 5 per centimeter cube. So it's a minority. So it's a very smaller concentration of the electrons. Right, so we need to create an electron channel and we need to accumulate the electron concentration, not the whole concentration, where in between this source and drain, because this should be a channel of N type, not P type. So that's why I am saying that we need to create the electron channel, and that's why we should have the electron concentration and the whole concentration should be equal. Not it is 10 to the power 5. It has to be increased to the 10 to the power 15. Right, so we need to create an electron channel in between source and drain, right, and we need to accumulate the electron concentration over here, but not whole concentration. Right, so we define the inversion voltage such that this is VTH, and that electron concentration at the surface should be equal to the whole concentration. Right, so electron concentration should be equal to the whole concentration, but from our calculation it is 10 to the power 5. So this is a big challenge, right? But 10 to the power 5 should be reached to 10 to the power 15, and it will increase gradually to create the inversion condition. And what is the inversion condition? That is the threshold voltage of the transistor. How it will be created? By using the inversion condition, and inversion condition is nothing but the threshold voltage of the transistor. Okay, got my point. You all know that inversion layer, how it is created. We all know the threshold voltage because you have already studied this device part, this the semiconductor device part. So from the knowledge of that semester, I can say once again, that is, we can calculate the electron concentration, that is 10 to the power 5 per cc. But our whole concentration is 10 to the power 15. But in order to make the channel in between source and drain, we have to accumulate, we have to incorporate the electrons more. So electron concentration should be increased from 10 to the power 5 to 10 to the power 15, and this can be done to create the inversing condition, and this is nothing but the threshold voltage of the device. Right, so let's have a look of the energy band diagram and see that how beautifully it is happening. Okay, and I think that from this concept you should have the knowledge of the energy band diagram. What is your conduction band, what is your valence band, what is Fermi level, what is intrinsic energy level, what is band gap, everything. I think that you should have the knowledge for that, right? Okay, so let's come to that point, that is I think it's visible. Okay, that is, I am just drawing this part, and please try to draw this section according to my way. So this is your semiconductor. I think it's a p-type doped semiconductor, right? And how can you define semiconductor? Obviously, in terms of energy level, there is conduction band, there is valence band, right? And if there is no doping, what is your intrinsic energy level? Yes, this is the 50-50. This is in the middle portion. And how we can draw that? This is your EI. This is your EI, okay? And for p-type semiconductor, for p-type doped semiconductor, the Fermi level, this is a very important point to note. For p-type doped semiconductor, whenever we will draw for Fermi level, what will be the location? The Fermi level will be in the lower half of the band gap, and where it will be located? This will be located in this way. And this is your EF, because we are discussing about the p-type doped semiconductor, because we are discussing about the n-channel semiconductor, right? But if it is opposite, if it is p-type n-type doped semiconductor, yes, it will be the upper portion, it will be near to the conduction band. Okay, so and in this way we can say that, and what is the band gap energy of this p-type doped semiconductor? We all know that this is nearly equal to 1.12 electron volt at room temperature. Is showing? Okay, so from this picture, from this drawing, how we can define this kind of drawing? Here, just these two parallel lines I have drawn first, and this is nothing but indication of the p-type semiconductor. Then, if there is no doping, there is an intrinsic energy level. Okay, and what is the position of the Fermi level based on the p-type semiconductor or n-type semiconductor is like that, and it is to the lower half of the band gap. Right, so this is nothing but the semiconductor which has conduction band, which has valence band, intrinsic energy level, that is EI, which will be just in the middle of EC and EV, right? And the band gap energy, that is EG, will be at the room temperature, and the value is 1.12 electron volt. Okay, so the distance between these your intrinsic level and the Fermi level, you all have heard this term. So this is known as your bulk potential. I think that you have heard this term, and please try to relate all you have studied previously, right? Because I think that you all have forgotten this term. Okay, so this is a minimum expectation from your side. So please go through that section, what you have already forgotten, and try to interrelate each and every parameter, and this will help you a lot in your preparation, taking the preparation in the semester as well as your higher standard examinations, right? So these gaps. So this gap means the distance between your intrinsic energy level and the Fermi level is known as, this is bulk potential. This is bulk potential. And why I am talking about this bulk potential? Because from the expression, the smaller problems may come in a semester as well as in GATE. Okay, so that's why I want to just excite the nerves of your brain to that section, to that parameter, to that new abbreviation, new metrics that will excite you, that yes, we have a knowledge of that, and we need to brush up this knowledge, right? So bulk potential, and how you can define this bulk potential? Bulk potential is defined as this phi b, and that is equal to kT by Q ln. We all know that this is regular law, and it is NA by NI. Okay, so this is, we all know that this is the thermal voltage we have already discussed in a non-scaling factor, non-scaling parameter. And what is NA? NA is nothing but the doping concentration, right? So you can easily calculate the bulk potential if we know the all other parameters, all other variables, right? But when you have the intrinsic silicon, here it is a doped semiconductor, but without doping, we all know that without doping, the semiconductor is known as the intrinsic semiconductor, right? But that's why I am saying my next part, that when you have the intrinsic Si, because this is into extrinsic Si means silicon. It's so whenever we will talk about the intrinsic silicon, what will be the position of the Fermi level? Yes, the answer is the position of the Fermi level just top of this EI. right? Because there is no difference between EI and EF. Okay, so otherwise your EF will move to the upper whenever it is a n-type semiconductor. So we have all discussed in terms of energy band diagram what is n-type semiconductor, what is p-type semiconductor, and as well as for the intrinsic semiconductor. So again I would like to reflect that important points. For p-type semiconductor, the Fermi level will be the lower half of the energy band gap, or to the nearly to the valence band. For n-type semiconductor, it will be nearly to the conduction band, and for intrinsic semiconductor, it's just the top of the EI. So that's why there is no difference between EI and EF. Okay, and coming to the another important mathematical formula that I think that you all know, that the electron, how we can calculate the electron concentration, because we need that parameter. So electron concentration is nothing but denoted by N, and I think that you should be able to recall that N equal to Ni e to the power EF minus EI divided by KT. Okay. So whenever EF equal to EI, then N equal to Ni, right? N equal to Ni, and what is your P equal to Ni e to the power EI minus EF divided by KT. And by using these two formula, we can easily relate that NP equal to Ni square. So these formulas are basic formulas and that are needed. Okay, and one last thing I should mention, that for p-type silicon semiconductor, the distance between EI and EF is 0.3 electron volt, right? That's why I am writing over here. So this gap is generally how much amount? 0.3 electron volt in general. Okay, so if we discuss the energy band diagram from I think that after this no confusion. So coming to the upper part, for if we discuss the energy band diagram from the gate to oxide and to semiconductor, that I am drawn over here. That means from gate to oxide and that to semiconductor, it will look like, got my point? If we discuss the energy band diagram from this gate to oxide and to semiconductor, so what it will look like that? Okay, so what it will look like that? It will look like, I think this point is visible. It will look like this one. This is your semiconductor, this is your oxide, and this is your gate. Okay, this is your gate, and this is your oxide, and this is your p-type silicon. Why I am showing this diagram? Because here I will discuss an important parameter that is known as your work function. Every gate there is a work function. After this, we heard a new term, that is bulk potential. Not the new term, because you are all used to this term. But another new term that I will discuss, that is a work function. It's a very important concept, right? And this new terminology I am using, that is a work function, and it means that the energy difference between the vacuum level and the Fermi level. So what is your work function? Work function is nothing but work function is nothing but, I am just writing the definition. It means, here I am writing, it means the energy difference, okay, the energy difference between vacuum level and Fermi level. So it means that the energy difference between vacuum level and the Fermi level. So it's a very, very important concept. So what is work function? What is work function? It means the energy difference between vacuum level and the Fermi level. Okay, so it's already more time related, more time consuming video. So in my next lecture, I will discuss all about work function and along with the short channel effects by using the diagram. Okay, so till now please try to relate all about that I have discussed over here, and in my next lecture please stay tuned for that, to relate that how work function is created, how it works, and everything with the concept of the short channel effect. So till now please continue this session, please enjoy my lecture, and please try to understand what is happening, how it is happening, and from where the concept is coming. Okay, so for up to this, thank you so much.